Today I'm here to present you the AIDGE platform. AIDGE is a platform that aims at providing a solution for embedded AI. This platform is supported by the DeepGreen project. Here you can see all the different partners for this DeepGreen project, which are both academic and industrial. As it has been already presented very well, we cannot sustain forever the current state of AI, especially because cloud AI will reach its limits. And with more and more applications that become more and more mature, we will be able to switch to a more edge AI approach. And in order to do so and to scale up in maturity, we need tools, and these tools come in the form of a software stack. This is what AIDGE is about. It's about a full end-to-end framework stack that allow you to come from your favorite framework, for example, PyTorch, TensorFlow, load it in ONNX, then provide some optimization for your framework from your neural network. So either high-level optimization up to low-level optimization to mapping your neural network into hardware, and either do some code generation or hardware design. This framework AIDGE is open source and is hosted by the Eclipse Foundation, which aims at providing a very permissive license so that even the industrial, from France partners, but also European, can exploit the framework. As we'll see, the software is very light and modular, meaning that at each step we have a light core that represents the graph. So when I will talk about neural network, I will talk mostly about graphs. And then at each step of the toolchain, we'll use different plugins so that when you create your application, you use just what you need. So, as I said, we talk mostly about graph because the core functionality of AIDGE is optimizing the neural network, meaning optimizing the graphs. To do so, we have a very innovative intermediate representation in the form of a graph, which allow you to apply different optimization to your model. For example, here we can see that when we have, so we call it a producer. A producer is a node in the graph that produces data. For example, if we take a convolution node, the convolution will have weight and biases. These weight and biases will be stored in producers. Then we can do to these weights some memory format adaptation, for example, transposing it from an HWC format to an NCHW format. So this will be done with transposition. Then we can apply some quantization factor, conversion to unexpected types with a casting, and then some memory layout transformation. All of these are nice, but if I want to see the graph, I just need a producer, so I can just fold it all with just a single line, which is the call to the constant folding function. And this is the core principle of AIDGE, is that at each step you can do very basic and simple graph transformation with just one line. This allows you to switch between representation. Here, for example, is an LSTM node. So LSTM is a long short-term memories node, which is particularly used in a recurrent neural network. And if you know what a LSTM is, well, it's the subgraph you can see on the left. So this subgraph is quite big, and either you can be, you will want to have the macro representation of just it's an LSTM node, or you will want to have a more fine-grained representation, which is this graph. And AIDGE, with this intermediate representation, aims at allowing you to switch from one representation to another very easily, always with one line. This intermediate representation is fully transparent, meaning that at each time you're working with an AIDGE graph, you know what you're manipulating. So I've already started to show quite a lot of figures of graphs. This can be done easily by generating a mermaid code that you can use to visualize your graph, which means that at every step you know how your graph is represented. We don't use, contrary to certain frameworks, compiled graph, which means that you always can see what you're manipulating. But also we support saving methods with JSON, which allow you to see all the attributes and the parameters of your neural network, meaning that you always know what you're manipulating. This graph is also multi-paradigm, so I will come back to this in a second. The main idea of this slide is to present that we have a structure in our framework, which is the intermediate representation, which is when we take a neural network, we represent it with a view on the graph. This view on the graph is composed of a set of nodes. The nodes representing the topology, meaning my convolution is connected to a bias and a weight, and is connected to another node. This node contains then an operator, so the node that contains the convolution operator, the operator representing the mathematical description of the node, which is a convolution possess, for example, a certain kernel dimensions and other attributes. And this operator then possesses an implementation. So this is a very software representation from a software standpoint, but it's very important to understand that we characterize all of these different aspects, the topology, the mathematical representation, and the implementation, in order for the user to be able to switch them very easily. So this way you can easily switch from a convolution with a CPU backend to a GPU backend, and you can easily manipulate your graph. The other aspect of doing something that is very modular like this is that in a lot of the current frameworks, you work only with tensor data, and with AIDGE, we aim at tackling some spiking neural network too. So this is where the multi-paradigm aspect comes from. The other aspect is the hierarchical graph representation. As I said, if you work on a graph, you may want to have just an LSTM operator, or you want to see the full subgraph of this LSTM operator. This is for optimization point of view. For example, if I want to merge nodes, etc., I may want to have a full decomposed graph. But if I want to just match one graph and map it to a processing element, then I may want to have a more macro view of this graph. This is done using a meta operator. So a meta operator is simply an operator that takes a subgraph and that implements this subgraph. So if, for example, when we have a convolution, in most of the frameworks, the padding is just an argument of the convolution, and in AIDGE, we support the padding as an operator, and we say that having a padding for a convolution is the combinations of padding then a convolution, and we represent it using just a meta operator, which means that we don't have an overload of information for the user. Finally, not finally, it's not the last one, but the generic aspect of the graph means that also you can create your own nodes and operators. Here, for example, I take a switch implementation, and you can easily create generic operators that you can then specify. And you can do so very easily using few lines of Python. Here, for example, you can see the code for a switch implementation, defining how to create it, how to create a forward with it. And then this is the last part, bind it to the operator in order to use it with AIDGE. And the last point, which is one of the main features, is the graph matching representation. So when I say that we want to manipulate and to optimize the graph, when I create a recipe to optimize the graph, I want to focus on a single part of the graph, a subgraph. And for example, if I want to fuse all the nodes that contain a convolution and a padding, I want to request to the graph give me all the com followed by padding. And this is where we created this regular expression syntax that allow you to match part of the graph, extract them, manipulate them, and then replace them back into your graph. And this allows for very easy graph manipulation. And this is one of the key strengths of AIDGE. And this is what allows us to do most of our optimization recipes. So I've talked a lot about graphs. The main framework that is used in AI for graphs representation is ONNX. ONNX is one of the key input of AIDGE, and this is why we put a lot of attention to having a good coverage. So at the moment we have more than 60 operators that are supported. For reference, there is something like 120 operators, so halfway there. But this allows us to support most of the CNN and vision transformer, for example, models. This comes also with a lot of integration with ONNX runtime for the test suite. And we also have a program with Saint-Exupéry, IRT, for the certification of the ONNX framework with SONNX, the goal being to be able to create a standard that is certificable, and to have a reference implementation using AIDGE in order to have a certification of the different operators. And yeah, the last part, always about the user interface. If you create your own ONNX operator, you can easily implement it in AIDGE, always with a few lines of Python. So here you can see you just have to create a new class or new function and then use a simple decorator in order to register it to AIDGE and to use it in your script. Once you've loaded your ONNX model, you want to know where the bottlenecks will be in order to optimize them. And this can easily be done using a rich analysis tool library that we have in AIDGE. For example, here we have a DNOV2 model, and you can see all the computing peak of the model, so that you can easily know where there's a need for optimization. Talking about optimization, we also provide a lot of methods, going from, for example, quantization with post-training quantization and quantization-aware training methods that are embedded in the framework. Quantization-aware training is coming in the next release that will come in 3 weeks. And at the moment we have state-of-the-art performances, and of course one of the main objectives of AIDGE, and the reason why I present it here, is to also beat the state-of-the-art and to accelerate the research, and the point where we create a new algorithm and the point where it's usable for industrial partners and to, yeah. And talking about this, we have the compression framework of AIDGE, which embed an algorithm that has been developed during the Holy Grail program. And here we can see that we beat the state-of-the-art, meaning here the AMET framework, which is the framework used by Qualcomm to deploy a neural net model to their hardware target. So here is an example of how AIDGE can accelerate going from I have a state-of-the-art method and now it's available to the broad public. Once we have done some high-level optimization to our code, we want to generate code in order to target our hardware. To do so, we use text-based templating using Jinja, which means that with simple lines of code, so example here, the scheduler export, you provide as an argument the library you want to export to. So here it's the lib C++. So this lib is a very generic C++, no optimization, no intrinsic used. And just this line of code will use a different template and generate the code that then you can put on your hardware target. This is done using, again, a very simple registration system, which means that if you want to implement your own kernels, you can easily register them using a simple Jinja template. These kernels will, of course, be able to be optimized. So here, for example, we do some optimization at compile time, and we are working on different export for more specific hardware and using more specific intrinsic, for example. Once we have our specific kernel, we want to adapt the graph to this kernel. For example, when I have a representation, mostly the data format, again, is NCHW. But when we're working with hardware, we want to work with NHWC representation. How do we adapt this? Well, once again, one line of code, adapt to backend, and this will introduce transpose operators and change your graph so that your graph remains valid with the new implementation you've coded. This adaptation is done so in order to adapt to your kernels, but you can also adapt the representation again to a finer grain representation. Here is the example where we take a convolution and then we can split it into a matrix multiplication view. This allows, for example, to do a more optimization, like fusing different nodes, etc., and having a different view which allow to do this kind of optimization. And finally, we can adapt the graph to match the hardware target. For example, the tiling. So for those of you who don't know, so tiling is splitting the input of the node into different strips. So for example, we have an image, and so we'll do vertical strip, and we'll load this vertical strip one by one to the node. This allows, in a constrained memory hardware, to still be able to run the network, even though the base graph will be too big. So this kind of adaptation allows to fit the architecture we're targeting. In order to map this, we have an orchestration model using a scheduling system, but also a memory model that allows us to map efficiently the memory of the graph neural network. All of this, so I will be quick with the perspective and the conclusion. So we want to support SNN, as I said, and we aim at doing more optimization, better code generation using more specific kernels, and to create a large ecosystem with both industrial and academic partners in order to accelerate all the research. Thank you for your attention. And if you have any questions, I'll take them.
Question? Yes.
Thank you for your presentation. Just want to know, like, how does this compare to something like TensorFlow Lite? Because there seems to be a lot of similarities in the goals of both projects. So I would like to know, like, what exactly is specific in this project compared to TensorFlow Lite?
So that's a good question. So as I said, TensorFlow Lite is a user compiled graph which is not accessible to the user. So this is one of the main aspects where we're differentiated. The other aspect is still about the white box aspect, is that instead of generating binary, we generate C++ code, which allow to better specify and to like if you want to certify about certification, it's easier to certify C++ code rather than a binary. And from a benchmark point of view, at the moment we don't have a lot of numbers. I think there was one of the kernels that was doing like, I think, yeah, compared to TensorFlow Lite, we've done some benchmark, but we're at the 1 year development, 1.5 years. So we haven't yet released all the different benchmarks regarding performances.
Another question? Okay, thank you. We are